Welcome to learn data structures and algorithms course. We are discussing unit number 4, design of algorithms. In the last session we have discussed how to design the sum of n numbers which are stored in an array, and we have discussed the iterative approach to solve the sum of n numbers stored in an array, and the recursive approach we have discussed. Finally, we have discussed the recursive sum a array comma n is equal to recursive sum a array comma n minus 1 plus a of n. This is the case when n is greater than 0, and this is equal to 0 when n is equal to 0. We have separated the nth element in the first call. Recursive sum of a comma n is equal to recursive sum of a comma n minus 1. Same function name appears in the right hand side. So this is said to be a recursion. A of n is separated. This is the case when n is greater than 0, and when n is equal to 0, what happens? We need to terminate the recursion. To terminate a recursion, we have called or we have returned a value 0. 0 is to be returned. We can solve this recurrence relation to verify the recursive relationship works correctly or not. So solving this recurrence relation, solving this recurrence relation, recursive sum, consider the left hand side, recursive sum a array comma n is equal to recursive sum a array comma n minus 1 plus a of n. Let us call this as equation 1 and the termination condition as equation number 2. Now 1 implies recursive sum of a comma n is equal to recursive sum of a array comma n minus 1 plus a of n. Initially here in the first call, n is the actual parameter. Here the actual parameter n is used to invoke the recursive sum a array comma n. This calls the first recursion here, recursive sum a array comma n minus 1 plus a of n. Here now this is the next recursion. In this the actual parameter is a array comma n minus 1. Now in equation number 1, put n is equal to n minus 1. Substituting n is equal to n minus 1 in equation 1, we have recursive sum a array comma n minus 1 is equal to n is substituted as n minus 1. In the right hand side, putting n is equal to n minus 1, we have recursive sum a array comma n minus 2 plus a of n minus 1. This is the actual value of recursive sum of a array comma n minus 1. Now in equation 1, 1 implies this equation, in the right hand side of this equation number 1, let us substitute the value of recursive sum of a array comma n minus 1 to this quantity. So substituting here, we have a recursive sum of a array comma n minus 2 plus a of n minus 1 plus a of n. Now in the right hand side, a recursion is occurring, a recursive sum a array comma n minus 2. Now once again write a substitute n is equal to n minus 1 in this equation, or putting n is equal to n minus 2, put n is equal to n minus 2 in equation 1. We have the quantity recursive sum a array comma n minus 2, that is equal to n minus 2 minus 1 n minus 3 plus a of n minus 2. So writing here recursive sum a array comma n is equal to, what is the final right hand side, recursive sum a array comma n minus 2, recursive sum a array comma n minus 2 plus a of n minus 1 plus a of n, a of n minus 1 plus a of n. Now recursive sum a array comma n minus 2, for which substitute n is equal to n minus 2 in 1, we have recursive sum of a array comma n minus 2. This is equal to recursive sum of a array comma n minus 2 minus 1, this becomes n minus 3 plus a of n becomes a of n minus 2. So substituting the value of recursive sum of a array comma n minus 2 in the right hand side of this equation, here we have recursive sum a array comma n minus 3, recursive sum a array comma n minus 3 plus a of n minus 2, a of n minus 2 plus previously a of n minus 1 plus having the next term a of n. Now the actual parameter is recursive sum a array comma n minus 3. So in equation 1, substitute n is equal to n minus 3, you have recursive sum a array comma n minus 4 plus a of n minus 3 plus a of n minus 2 plus a of n minus 1 plus a of n. So substituting here, this goes like this. One stage when the actual parameter recursive sum a array comma the second parameter, that becomes 1. What happens? Recursive sum a array comma 1. Have a look into here, n means the next term here, n minus n means here initially n means recursive sum of a array comma n means recursive sum a array comma n minus 1. Recursive sum of a array comma n minus 1 means recursive sum a array comma n minus 2. Recursive sum a array comma n minus 2 means recursive sum a array comma n minus 3. So likewise next term recursive sum a array comma n minus 3, that means you have the right hand side recursive sum a array comma n minus 4. So this way the terms are going. Now starting from right to left, a of n minus 1 etc., a of n minus 1, then a of n minus 2, then here a of n minus 1, a of n minus 2, a of n minus 3. Here n minus 2 means n minus 2 plus 1, that means n minus 1. N minus 3 means n minus 3 plus 1, what happens? N minus 2, right, the next term. So here 1 means what happens? 1 plus 1 is equal to 2. So writing here a of 2 plus etc. Plus a of n minus 2 plus a of n minus 1 plus a of n. Now writing here recursive sum a array comma 1. How to find a value of recursive sum a array comma 1? In equation 1, put n is equal to 1. So substituting n is equal to 1 in equation 1, we have recursive sum of a array comma, here n is 1. 1 means what happens? Recursive sum a array comma 1 is equal to recursive sum a array comma n minus 1. A array comma n minus 1 is 1 minus 1 0 plus a of 1. This is the value of recursive sum a array comma 1. Now substituting the value of recursive sum a array comma 1 in this equation, we have recursive sum of a array comma 0 plus a of 1 plus a of 2 plus etc. The last term is a of n. Now in this recursion, recursive sum a array comma 0, what happens? Equation 2, recursive sum a array comma n is equal to 0, return 0, right, when n is equal to 0. So applying equation number 2, since from 2 recursive sum of a array comma 0 is 0, then writing the remaining expression a of 1 plus a of 2 plus etc. a of n, we have the sum of the array entries a of 1 plus a of 2 plus a of 3 plus etc. plus a of n. This is the actual value of left hand side recursive sum a array comma n. So clearly the algorithm recursive sum a array comma n finds the sum of the n elements which are stored in an array. That is what here in the right hand side we have this expression s is equal to a1 plus a2 plus a3 plus etc. an, right. So the entire expression is evaluated and the result is assigned to the left hand side. Since the left hand side, right, the function call recursive sum a array comma n, this function call exactly finds the sum of n elements stored in an array. So we are verifying the correctness of the algorithm. So clearly this recurrence relation works correctly. The next problem is, let us design the algorithm to find the factorial of the given integer. Second problem, design an algorithm find the factorial of the given positive integer. We know that n factorial is equal to 1 into 2 into 3 into etc. n, and 1 factorial is 1 and 0 factorial is 1. Since n factorial is equal to 1 into 2 into 3 into etc. 1 into 2 into 3 into etc. n, we need to find the product of the first n natural numbers 1, 2, 3 etc. n. 5 factorial is 1 into 2 into 3 into 4 into 5. 8 factorial is 1 into 2 into 3 into etc. 8. We need to design the algorithm to evaluate this equation. N factorial is equal to 1 into 2 into 3 into etc. n. As we have designed, right, the algorithm to find the sum of first n, or algorithm to find the sum of n numbers which are stored in an array, there we have summed, right, the corresponding array entries. Here we need to find, right, the product of integers. To find the product of the integers, let us initialize one variable, say fact is equal to 1. Then over the range of some I, right, for I is equal to 1 to n, do. What we have to do, we need to update a variable fact by multiplying fact with the current I. So writing the assignment statement, fact is equal to fact star I over the range of I is equal to 1 to n. When fact is equal to fact star I is evaluated, finally the variable fact assigns 1 into 2 into 3 into etc. n, so that the value of n factorial is computed and the result is assigned to the variable fact. In case if the input is the positive integer, right, n is greater than or equal to 1, the logic works correctly. In case if n is equal to 0, explicitly it should be controlled, right. If n is equal to 0, then return 1, else we need to find, right, the value of fact using this logic. Fact is equal to 1, for I is equal to 1 to n, do fact is equal to fact star I. Finally we need to return the value of fact, return fact. This is the iterative logic, iteration. This is the iteration logic to find the factorial of the given a positive integer. Now let us design the algorithm to find the factorial of the given positive integer. Algorithm factorial n. What is n? N is the formal parameter, n is the formal parameter, n greater than 0, n is an integer, that means n is a positive integer to which the value of n factorial, right, should be computed. N factorial is equal to 1 into 2 into 3 into etc. n. This equation should be computed. The algorithm returns a value of fact, right. we can write in a comment, return the value of n factorial. Algorithm returns the value of n factorial. N greater than 0, that means n is a positive integer. Having the statements initializing fact is equal to 1, then control through the for loop for I is equal to 1 to n do. Writing the computational statement, fact is equal to fact star I. For ends with loop or end for. Finally, return a value of the computed variable fact, return fact, closing curly brace. This defines end of algorithm factorial. Since n factorial is equal to 1 into 2 into 3 into etc. n, we need to find the product of these integers. Hence, initializing one product variable, let it be fact. Fact is set to 1 over the range of I with an initial value of I is 1, final value of I is n. Initial value of I is 1, I is equal to 1. Final value of I is n. A default increment is this is 1. For each value of I, the variable fact gets updated. Fact is equal to fact into I. So when I becomes 1, current fact is 1, 1 into I, right, 1 into 1 is stored into the variable fact. When I becomes 2, current value of fact is 1 into 2 is updated in a fact variable. When I becomes 3, already 2, right, fact is 2 into 3, 6 is updated in a variable fact. So likewise, when I becomes n, the product of n natural numbers, say 1, 2, 3 etc. n is computed and the result is assigned to the left hand side variable of fact. Finally, the algorithm returns the value of variable fact. Now let us trace this algorithm. Trace the algorithm for n is equal to 5. What is the initial call? Initial call is factorial of n. Factorial n. The value of n is 5. That means factorial of 5. Five is the actual parameter. In the function algorithm factorial, the variable n receives 5. N receives 5. We need to trace these statements. Fact is equal to 1. These are the well defined instructions. Fact is equal to 1. For I is equal to 1 to n do. Fact is equal to fact star I. Finally, return a value of fact. So, to find out this trace, let us construct the columns I, checking the value of I less than or equal to n, then fact is equal to fact star I. Initially, the variable fact has been set to 1. So, without, right, or before entering the for loop, initial value, right, initial value of fact is set to 1. Then when the control enters into the for loop, what happens? Initial value of I is 1. Next, it checks the condition if I is less than or equal to n. I is 1, 1 less than or equal to 5, condition is true. 1 less than or equal to 5, condition is true. Now, the statement to be executed is fact is equal to fact star I, current fact is 1, 1 into 1, 1 is updated in the variable fact. Next, I is incremented by 1, I is equal to I plus 1, this implies I becomes 2. For the next value of I, the condition to be tested is 2 less than or equal to 5, condition is true. Update a value of fact, fact is equal to fact star I, current fact is 1, 1 into 2, I is 2, 1 into 2, 2. Next, I is incremented by 1, I is equal to I plus 1, this implies I is equal to 3. When I becomes 3, the condition to be tested is 3 less than or equal to 5, condition is true. Fact is equal to fact star I, current fact is 2, 2 into 3, 6, fact is updated. Then I is incremented by 1, I is equal to I plus 1, I becomes 4. Checking the condition if 4 less than or equal to 5, condition is true. Now, the statement to be evaluated is fact is equal to fact into I, current fact is 6, 6 into I is 4, 24, then I is incremented by 1, I is equal to I plus 1, I becomes 5. Checking the condition 5 less than or equal to 5, condition is true. Now, evaluating current fact is 24 into current I is 5, 24 into 5, 120. Now, I is incremented by 1, I becomes I plus 1, I becomes 6. When I becomes 6, checking the condition if 6 less than or equal to 5, condition is false. Here what happens? Control completes the execution of for loop. Now, the control has to come out of for loop and the statement to be executed is return fact, return fact. Current value of fact is 120, this is equal to 1 into 2 into 3 into 4 into 5, this is equal to 5 factorial. Is computed, finally return fact, the current value of fact is 120, this is equal to 1 into 2 into 3 into 4 into 5, this is equal to 5 factorial. So, finally, the variable fact holds 120, this is equal to 5 factorial, hence the algorithm returns the value of 5 factorial for n is equal to 5. In case if we input n is equal to 10, the algorithm finds the value of 10 factorial. N is equal to 20, the algorithm finds the value of 20 factorial. So, in general, right, whatever the value of n as a positive integer, the algorithm finds the value of n factorial, which is equal to 1 into 2 into 3 into etc. n. This is the iterative approach to find the factorial of the given positive integer. The iterative approach can also be designed or converted to the equivalent recursive approach.